Hi, my name is Ming-Hsuan. I would like to thank the organizer for inviting us to give a talk. I will cover the first part and Boqing Gong will cover the second part. So over the year, my group has been working on different tasks to learn from imbalanced visual data. And in that, we have developed algorithms to detect objects, to track objects, segment objects, and recognize objects. And the overall general theme is that we find useful positive and negative examples. For example, for different tasks. For example, for gender classification, we can easily find a positive example, but it's not so easy to find useful negative examples. And likewise, for tracking, it's easy to find positive examples, but it's not so easy to find useful negative examples. So in that, we have developed different methods for that. And you can also develop different classifier from bagging, boosting, ensemble, and cascade classifier. And you can also change your learning objective function and reweight the samples. And today we are going to focus on recent approaches on domain adaptation and feature learning for semantic segmentation and object detection. So the first one I'm going to talk about is how to adapt learned model for semantic segmentation. So we all know that for raw outputs from semantic segmentation, the results are often noisy and it often require some smoothing, either with CRF, spatial propagation, and so on and so forth to smooth the results. But we also know that for the training and data test sets, no matter how different they are, the spatial layout should be very similar. In other words, we can exploit structural output. But we also know that there is an imbalance between training and test data sets. And one approach to adapt the train model for new data set is to use domain adaptation. So in that, we develop one effective method for that. So the problem setup is pretty straightforward. We can get the free labels from synthetic data, and then we can train some model to give labels to each pixel in the test image. However, the domain gap is large, and so we need to find some way to narrow the domain gap. But as I mentioned a while ago, the spatial layout, no matter whether they are from synthetic image or real images, should be similar. For example, their tree should be next to the sidewalk, and the sky should be on top usually, and cars should be on the road, and so on and so forth. So the output is structure. So we want to exploit such property for semantic segmentation. And to narrow the domain gap, one way to do that is to use domain adaptation. So one common way is to do feature alignment on the feature label. So what we do is that you take a source image and take target image, and you have some encoder fitting to that, and then you can apply some alignment on that. And on top of that, you can also use adversarial learning for that too, so that you can train the generator and discriminator for better results. However, the feature space is usually large. Depends on network you use, usually thousands of features. So it's not so easy to align features. In this work, what we do is that we directly align the structural output. So instead of using the feature space, we use the output space. And for that, we can align them better, and it's more effective to do that. And in addition, we can also apply the same method on multiple labels. So that's the main ideas. For details, you can check our papers. By doing this, then we can effectively narrow the domain gap. For example, here we train on get GTA5 data set and test on CDX gap. And these are some other methods, including Cicada, and either on feature label or pixel label. And ours is, with our method, we can achieve significant performance gain. In addition, we can also Here we use we use VGG16, and we can also use a stronger backbone network for that. And here are results that we can obtain using ResNet for that. And again, we can use our method with single level or multiple level, and we can obtain significant performance gain. So here we look at that whether our method can achieve or can perform well on different setup or not. So we compare with our bound, say you have all the labels and train that. And so that will be the oracle. And if you look at all the methods, they perform pretty well if all the labels are given. However, for the other methods, when the target labels are not known, then the other methods do not perform that well. And we also look into a sensitivity analysis on method because there's a free parameter, and overall our method performs reasonably well. You can choose it performs well within a wide range of parameters. And here we show the result on training on sincere dataset and test on cityscape dataset. Again, compared with the stereo method, then our method performs reasonably well. We also train on different dataset on full city, and then we can, here again, our method perform pretty well against the stereo method. Here are some visual outputs. So you can see that as we exploit structural output, the results are smoother without using additional smoothing methods. And so here on top, I show you the result without using adaptation. Below here, we show you the result with our structural output adaptation. As you can see that here, the results are smoother. And again, we do not use any actual smoothing method to do that. So in this work, the main idea is that we apply adversarial learning on in the output space. And we also have a multi-level objective function for that, and it performs reasonably well. And the code and train model are available on this website. The second work I'm going to talk about is also on domain adaptation. So here, the idea is this. So we want to develop, we want to use cross-domain consistency to narrow down the domain gap. So, and the performance can be applied to semantic segmentation, depth estimation, or optical flow. So as I described a while ago, for domain adaptation, one way to do that is to apply a feature alignment. And we can, so another way to do that is to operate on the pixel level. You can synthesize the result and compare with the output. And you can train a discriminator and generator for that. Yeah, another way to do that is to apply both feature level and pixel level adaptation. So in this Cicada method, what they do is that you have source image, then you can train a translator or generator, and then you can synthesize the result in the target domain. And for that, you can also train another translator back to the source domain, and then you can compare with you can compute the reconstruction error. In addition, you can also compute the consistency between the semantic segmentation outputs. And in addition, they also operate on the target image. For this stylized image or translate image, you can also use the target image and the computer Gong loss. So so it operates on both pixel level with 4 losses and also another one, the traditional one on the feature level. So this is what they do in the Cicada method. So in this work, what we do is that we want to enforce, we can translate from source to target and from target to source. And then we want to enforce one consistency loss. So what we do is this, given the source image, we can train a generator to the target domain. And likewise from target domain, we can train a translator to the source domain. And so we have a pixel level adversarial loss. And likewise, we can fit into the encoder, and then we can apply the standard feature alignment so that we have another loss function on the feature level. And for the task at hand, which is semantic segmentation, then or sim parsing, so then we want to make sure that no matter whether they are from the source or the target, for the source image we have a test loss, and for a translate image we also have a test loss. We want to make sure they are consistent, and in addition we also have cross consistent loss here. So basically we want to make sure that once an image is translated from target domain, and when it's applied to the task, that the loss will be consistent with the original target image. And for testing, then basically just fits through the encoder and apply to that. And so for detail, you can look up our paper. So we apply the same method for different tests: semantic segmentation, depth estimation, and optical flow. And the main idea is to apply cross-domain adaptation. And so here result we compare with state-of-the-art method, and we can use we train on GTFI and test on Cityscape, or we train on Cynthia and test on Cityscape, and we can obtain significant improvements. So here are some visual outputs. So basically here, these are inputs, and these are ground truths, and these are without cross-consistent loss, and this is with cross-domain consistent loss. And here are some more results on different data sets. And likewise on depth estimation, and also from optical flow. For details, please check our paper. Okay, so in this work, the main idea is to use cross-domain consistency, and this is application agnostic, and we achieve state-of-the-art result. So I'll use 2 minutes to present our recent work on cross-domain feature classification using feature-wise transformation. So the main idea is that we want to develop feature learning for that. So given a support set and label, then we want to see how we can adapt to the unseen query data set. And this is well-known problem with long tail, which is the main theme of this workshop. So there are several approaches. So in this work, we focus on metric-based approach. So in general, the idea is that you have a support set and query, and then you apply to the feature encoder. And then the main idea is to use feature metric function to see how to bring them together and how to infer the result. And all the methods are different in the design of metric function. So, but metric-based methods do not perform well when the domain gap is large. So that's the main focus of this work. For example, if we train on a mini image, if we use a mini ImageNet for training, and then we test on CUB data set, which is a fine-grained BERT data set, the domain gap is quite large, and the metric methods do not perform well. For example, here are results shown by other methods, by some other researchers. They have shown that, okay, if we train on ImageNet and then test on CUB, the performance drops significantly. So in this work, what we want to do is to apply feature-wise transformation, and so that we can adapt the model to unseen or to the target domain. So what we do is that we apply on each feature label, we apply a simple feature transformation so that we can align them well. And for detail, you can look our paper. So the feature-wise transformation is based on alpha transformation, and there are 2 main parameters, gamma and beta. And so the main idea is, but these are governed by 2 hyperparameters. So the main idea is how to estimate these hyperparameters for unseen data set. And so we develop one learn-to-learn method so that we can we can adapt the parameter well. So the main idea is that with given domains, we sample a pair of domain and we optimize parameter of a metric-based model with a feature-wise transformation using the pseudo unseen data set. And then we remove that and see how it performed well. And then we update that. We update parameter using the pseudo unseen data because it indicates how well it adapts. So yeah, so the first thing we choose a pair and then we can train a feature feature transformation, and then we remove that and then we test on the unseen data set and see how it performs and update the parameter. And so we use the mini image data set, CUB, cars, presets, and prenet data set for that. And so there are two scenarios. One is the one-on-one. So basically we train on one and test on the other. The other one should leave one out. So basically we put everything together and leave one out for test. And then we use both learning. So this we will have pairwise. We will pre-selected pairs. And then here we have we need to choose among two, and then and use learning to learn method to adapt to learn the parameter better. So here are result with pairwise feature transformation. So we train on mini image net and test on CUB and also on so forth. And here are the result without feature transformation or with feature transformation. Overall, our method performed reasonably well. In the second scenario, then we put everything together and then we leave one out. So we use all the other data and test on CUB. And then we can also use the original pairwise feature transformation, or we can use the learning to learn method that I briefly described a few minutes ago. And so basically the results show that with learning to learn, we can better narrow the gap and adapt the model better. And here are some more details. So you can look up our paper for that. So basically the main idea is that with learning to learn feature-wise transformation, we can achieve better result. And we also have some visualization result in the paper. The code and data set and train model are available on our website. So please look it up. And there are some more analysis and derivation in the paper. And so basically, we use, I briefly described some of our recent work on how to learn from imbalanced data set for different tasks. So that today I talk about domain adaptation and feature learning. And Boqing is going to talk about some of our recent work. Thank you.
Okay, welcome to the second part of the talk. I'm Boqing Gong from Google. I will talk about our recent work on long-tailed visual recognition. This is joint work with Matthew and Ming-Hsuan, my colleagues in Google. Mohammed Jamal, he's my former intern, and my collaborators Stella, Zui, Zhongqi, and Liqian. Let me begin by asking you a question. So if you ran experiments to study some research questions, which dataset do you prefer? Do you like ImageNet? It's fairly large, 1,000 classes, and all the classes are evenly distributed, both training and testing, balanced dataset. Versus the second dataset, which is AdNaturalist. It's also large, 5,000, I think between 5,000 8,000 classes. Unfortunately, the classes are highly unbalanced. Or to be more precise, it's they follow a long-tailed distribution. And you can see a small number of classes, they have a lot of training examples. But for a majority of the classes, we have only like 30 or 20 images, training images for each of the classes. Which dataset do you prefer? My guess is that most of you might choose ImageNet because it's really even dataset, all classes are balanced, easier to tune hyperparameters, easier to get results. Also, there are a lot of existing results you can compare with. But I would argue that we should probably go with the long-tailed analyst in the future. Here is why. If we check the existing datasets in the literature, including the sound dataset, which is also similar to ImageNet, it's collected deliberately for the place recognition. So it's roughly balanced across different places. But if we check the objects in this dataset, they follow actually a long-tail distribution. Why? Because we never tried to balance this dataset for different objects. Second example here is about Flickr image tags. All the tags, they are not equal. Some of the tags are very popular, and most of them actually only appear on a few images. The third example is the Google landmark recognition dataset. So for only a few number of landmarks, we can get sufficiently big training sets. But for a lot of other landmarks, we cannot get enough training images. So naturally, the landmarks, they also follow a long-tail distribution. This is just natural. This is nature we collected from the web. The very last example is Elvis from Facebook. This is an instance segmentation dataset built upon the Coco dataset. So one notable property is that it also has the long-tailed property. So given all of these, so they have something in common, which is that they are in the wild. Including this sound dataset, they are in the wild for the objects, not for the places. So when we try to study real problems in the wild, the long-tailed distribution is something we really cannot overlook. One good thing I know in our community is that we have really a lot of interesting stuff we can study, such that maybe for some time we can just ignore this elephant in the room and focusing on some other interesting stuff to do our research. But the more we advance our field, the more we want to solve real problems, the more urgent I feel that we should actually explicitly study the long-tail distribution. We should study it for not only object recognition, but also object detection, instance segmentation, and so on and so forth. So given that argument, hopefully you agree with me that if we want to move the field even further, try to solve the real problems in the wild, we should formalize this long-tailed recognition problem into a standalone problem, such that we can develop new techniques to resolve this issue, which appears in all different visual recognition tasks. So we studied this problem in 2018, between 2018 and 19, and we defined 3 benchmark datasets using existing datasets. So they are fairly, I would say fairly medium-sized. The reason is we want to have the medium-sized datasets so that not only researchers in industry, but also from academic research labs, we can all study this problem using a fairly representative, but not too big dataset to study the problem. In the paper, we also proposed a fairly straightforward approach using memory bank to enhance the tail classes. Okay, so that was one paper. Until now, hopefully you might started to think that, okay, then maybe long-tailed recognition problem is something interesting. It's something we should study. But what's new in this problem? Because in machine learning or in data mining, This so-called imbalanced classification has been there for a long time. It's really a very old AI problem. It's nothing new. What's new actually is not on the first half of this long-tailed curve. It's on the second half. So for a lot of classes, we really only have a few, like 10, 20, 30 training images for them. We cannot see that from the traditional imbalanced classification problem. Instead, we see those kind of like 20 or 30 training images per class. We see those scenarios happen in new AI problems like few-shot learning, transfer learning, or meta-learning. So this long-tailed curve is really a nice vehicle that connects the old AI, the imbalanced classification, and the new AI problems like meta-learning and few-shot learning. Okay, so we can, so that's one way to see why this is a new and interesting problem. Another way of studying this problem is from the lens of domain adaptation, because I work on domain adaptation. That's so when I was reviewing the literature, and especially the papers published over the last couple of years, when the work published on solving this long-tailed visual recognition. So I tried to analyze those from the perspective of domain adaptation. In domain adaptation, we have two different domains. The data, they follow different underlying distributions. So in the long-tailed scenario, we got a training set whose classes follow a long-tailed distribution. We know that. In most of the cases and testing stage, however, we actually have a balanced dataset. This is a reasonable design because we want to have not only high-performing models, but also high-performing models which can perform equally well on all classes. We really want to have an unbiased model. So naturally, we can consider that we have two different domains. One that we got data drawn from a long-tailed distribution, the other that we got data from uniform distribution or roughly uniform distribution. Our goal is always to get a very small error in the targeted domain, which is, roughly uniformly distributed. But in training, we only got a long-tailed training set. So in order to write down from this equation to this one, we need a factor like this. We can decompose the distributions into a marginal distribution over classes and a conditional distribution of images given that class. Okay, so furthermore, we denote the terms here in the blue color by omega y, and we denote by 1 plus epsilon here by and the term in the red color. Okay, so now we can use the equation here to analyze the existing work. Roughly, they all try to have different methods to estimate the omega y. They never tried to estimate epsilon, but they assume epsilon is 0. But we feel that's not true for tail classes at least. Because for some common classes like cats, they appear, they are definitely one of the head classes. So we got a lot of training images for cats. So roughly you can imagine, therefore, the distribution of the training images is a fairly good representation or estimation of the distribution and the testing stage, because we got a lot of images from this distribution. So it's probably okay to assume that epsilon is 0. But for the tail classes, the scenario is different. We only got a very few number of images. That's not a very good estimation of the real-world scenario. So we don't think it's a good or faithful representation of the testing stage distribution. So we cannot assume it's 0. So following this reasoning, we summarize our analysis from the domain adaptation perspective into a CVPR paper published this year, and we proposed training algorithm. We feel it's fairly straightforward. So basic idea is first we train using traditional cross entropy to train the network for certain epochs. After that, we try to weigh the loss functions by not only a term for each class, but also a term for each training image. Of course, we don't know how to do that, so we assume that we still start from zero, a zero weight for each of the training images, and then we run a one-step update to the neural network. After that, very similar to the meta-learning framework, we got a development set, we call it, or you can call it a validation set. We use this validation set to evaluate how good the one-step updated network is by this error. So this error tells us how to update the epsilon, which is the weight for each images, such that we can arrive at a lower validation error. So that's how we get the weights for the training images. With the weights, therefore, we can get a much better one-step update to the neural network. So we can run the procedure here again and again until it converges. The results are fairly good on 6 benchmark datasets here, and you can see we got both small-scale datasets as well as the real datasets, the Analyst 2017 and 2018. The results and the moment we published the paper, I think definitely the results on 6 benchmark datasets are all state-of-the-art. Here I highlight some results on CIFAR 10. We got a good improvement for the traditional cross-entropy loss. We also observed good improvement over the focal loss and the large margin loss. Okay. Further investigation into the details tell that the approach works here ours by not only improving the performance of the tail classes, but also it improves a little bit for the performance of the head classes. In contrast, a closely related approach to ours, it can improve the performance on the tail classes, but it hurts a lot. It hurts the head classes a lot. So by the way, here, sorry, those are confusion matrices. I should have explained that earlier. So each row is a class, and each column is also a class. Okay. Yeah. A little bit detailed analysis tells that for the head classes, like a class 0, class 3, the weights we learn for each training image, they are very small. But for the tail classes, like a class 9, and you can see here, they are pretty big. Meaning that indeed our analysis makes sense. That meaning that the tail classes, because we only have a few number of training images for each of them, they are not very good representation for the testing distributions. We need to weigh not only the classes, but also the training images to get a good estimation about the testing risk. Okay. We also ran a lot of ambulation studies. I feel we should probably skip them to save the time. Instead, let me elaborate on this slide a little bit. First of all, hopefully by now you agree with me that long-tailed visual recognition it's worth studying by itself. It should be a standalone problem especially when we try to advance the field further into the real world. No matter what we do, object detection, segmentation, when the number of classes we are interested in become really large, the long-tailed phenomena emerges. So we have to study this problem, and we have defined a few benchmark datasets to facilitate the research in this problem. Also, we provided a domain adaptation perspective to understand this long-tailed visual recognition problem. So our take is that the old techniques for the old AI problem, like imbalanced classification, might be useful for handling the head classes. But for the tail, we really need more recent techniques, including the meta-learning or domain adaptation techniques like domain invariant representation learning, curriculum learning, adversarial learning, data simulation, and so on and so forth to handle the tail classes. I'm really excited by this problem and look forward to further development in this subfield. Thank you.